Welcome to everybody to this inaugural event of the Middle East and South Asia Quantum Computing Meetup Group. This is the first event officially of this meetup group. We've had a organizational meeting, which was back in August last year. We've had a couple of, or maybe 3 events that we cross-listed from the Washington, D.C. meetup group, our friends who we are collaborating with, and through whom we've had developed a connection with Association Quantum, and Association Quantum is our sponsor as well as Washington, D.C.'s group. Today we have Steve Reinhardt and Mark Wainger and Raouf Dridi from Quantum Computing Inc., which is a company that is working in the area of software development for emerging quantum hardware platforms. So we'll hear more about that from these gentlemen. Let me just introduce you briefly to these gentlemen here. Steve Reinhardt joined QCI, Quantum Computing Inc., in May 2019, and he's the lead. He joined to lead QCI's development of quantum-ready applications and tools with a focus on delivering differentiated performance using quantum concepts on classical computers and on hybrids of quantum and classical machines. He has nearly 40 years of senior level experience in software and hardware engineering, development, and innovation. Prior to joining QCI, he was Director of Software Tools and Custom Applications at D-Wave Systems, the world's first commercial supplier of quantum computers. At D-Wave, he led teams involved in developing quantum computing tools like QB-Solve and worked with customers to map out problems for effective execution on D-Wave's quantum annealing-based quantum computer. Before that, he served as Vice President of Joint Research for Interactive Supercomputing Corporation, where he secured funding for projects to implement advanced graph analytic capabilities in STAR-P. He has also served as Chief Engineer at Silicon Graphics, where he led a development of Altix, a scalable shared memory Linux-based system that generated revenue of more than $600 million. Before that, he served as the project director for Cray Research and produced a distributed memory supercomputer, which generated more than $700 million in revenue for Cray. Steve has a Bachelor of Science in Computer Science from Yale University and Master of Biological Sciences with a minor in Bioinformatics from the University of Minnesota. Let me introduce Mark Weinger now. Mark has more than 35 years of innovation and entrepreneurial experience in computer and information technology, finance, and banking. He has been the co-founder, chief executive officer, and chief technology officer, and director of a number of tech-focused companies. Prior to joining QCI, Mark served as a technology system consultant for domestic and international enterprises, including establishing an online brokerage firm, structuring collateralized debt obligations for a major Dutch bank, analyzing Brazilian asset-backed securities, and designing a bank balance sheet management system. Mark has a Bachelor of Science in Chemistry and Physics from MIT and a master's degree in Applied Science from New York University. Finally, let me introduce Dr. Raouf Dridi. Raouf is a senior developer at QCI. Prior to joining QCI, Raouf was a senior research associate at the Carnegie Mellon University Tepper School of Business, and he was a research scientist at the company 1Qubit. Raouf has a PhD in mathematics from University Lille 1. I hope I pronounced it correctly, Raouf, but please correct me later, which is a French university. His research interests include topos theory, lambda calculus for languages for quantum computers, and algebraic geometric methods such as Grosvenor bases for programming quantum annealers. He has written a very nice paper on this topic related to factoring prime numbers on quantum annealers. And I suggest and recommend everybody read that paper. It's a nice paper. So with that introduction, I will now pass the mic to Steve, I suppose. Steve, would that be accurate?
Yes,
Okay.
yes, that's right.
All right, please take it away.
It looks like I need permissions to share my screen.
Sure. So I will go ahead and find you here. And I'll make you a host, I suppose.
Okay.
And
I promise not to do anything nefarious.
Good, yeah. There we go. See if that allows you to do that.
Wonderful, thank you.
Awesome.
Okay, let me go full screen. All right, well, good evening to you, those of us in the Middle East or South Asia. Thank you for joining us to hear about the webinar about the Mukai quantum acceleration platform developed by Quantum Computing Inc., QCI. Thanks to Faisal and Amalak and the other organizers for hosting today's webinar. And you already heard the speakers will be Raouf, Mark, and myself. So today we want to show you two practical demos of how to solve real-world constrained optimization problems using quantum computers. And that's really the first goal for the webinar. Our second is to find some of you who need the power of quantum computers, but don't have the time to learn the intricate details of programming quantum computers at a low level, and would be willing to pursue proof of concept projects with us. Please feel free to put questions in the chat at any point, and we'll try to answer those, whether via the chat or verbally at appropriate times throughout. So this is our agenda. I'm going to talk for a few minutes about Mukai Overview, and then Raouf will do a constraint optimization demo, and Mark will do a community detection demo. So Mukai and what it's doing. So at a high level, Mukai simplifies the use of quantum computers by applications. So this accelerates adoption of quantum computers. Everyone's excited about quantum computers. You are probably excited because you're here this evening. And everybody's excited about the potential, but of course there are challenges to delivering that potential. One thing that we are focused on is we have to scale to solve real world problems on quantum computers. And in our view, it has to be what we call subject matter expert APIs. And by subject matter expert, we mean a biologist or a chemist or a logistics person or whatever. They're not a quantum computing expert, they're an expert in something else. And we feel we have to do this to avoid lengthy and costly learning curve and rework if you approach with low-level APIs. Also, we feel like any programming method we're going to use has to port to a lot of QPUs, because it's really hard to know today which one is going to be best for which purposes. Also, given where we are today, there has been no quantum advantage, no superior performance demonstrated on a real world problem by a quantum computer. We see that it's really important to marry strong classical performance with strong early hybrid quantum classical performance. We need to retarget applications to quantum computers, and we need to minimize technological risk. So those are some of the things we have to do to make quantum computers real, in industrial and commercial context. So Mukai addresses that. So Mukai is a bridge to quantum for subject matter experts and application developers. No quantum programming expertise is required. You can transparently benchmark the same problem across leading quantum QPUs and strong classical solvers. And you'll be able to solve big problems with near-term QPUs with significant capability. As a developer, I only need to learn a few high-level APIs, and those APIs deal with concepts that I already know about. Things like constrained optimization, things like graph analysis. You have transparent access to a diverse set of QPU and CPU resources today. Today we support Rigetti, D-Wave, and IonQ computers, quantum computers, and there are several others in the pipeline to be released soon. You can also solve that same problem with no changes other than targeting a sampler on classical CPUs with superior performance using those same APIs. So that is, in a nutshell, that's what we're trying to do with Mukai. Another way to state that whole thing is, so I'm a person, I have, I'm a biologist or a chemist or a protein designer or whatever, and I have an application, and for whatever reason, there's a piece of it I think is relevant to a quantum computer. So what do I have to do today to solve my problem on a quantum computer? Well, as it turns out, there are a whole lot of things. Once I've found a piece that is quantum friendly, I have to do whatever I can to shrink or reduce or simplify that portion so that it takes best advantage of a QPU. I have to map that portion to a circuit or a QUBO, depending on which type of QPU I'm using. I have to create a near optimal circuit, just like classical compilers do for classical CPUs. And then I need to map to the native hardware. So what are the native gates? What's the qubit connectivity topology? I have to tolerate noise. I have to correct errors, blah, blah, blah. You kind of jump over here to the right. I have to find and use the best QPU for my problem. So we've got a variety of QPUs out there. We expect them to be, some to be better for some problems, some to be better for other problems. Which is which? It's going to be hard to know as a single person. And then the last one here I'd call out is, in the last 12 months, there have been 7 new QPUs announced. Actually, I should say available for public use. So that means I do all these steps, and then every 7 weeks, I have to target a new QPU to see how it does on my problem. Well, as you can see, this is a lot of work. Even for the brightest of people, this is a lot of work and time and money from a commercial point of view. So what Mukai does is it shrouds all this complexity with simplicity. So there's 2 key APIs we have. One is our constrained optimization API, which Raouf will demo. The other is our QCI Network X graph analysis API. When I have, so what does this buy me in terms of application development? Well, if we look at how long until I start working on to make use of a quantum computer to when I get results, if I use the lower level toolkits, I need to learn the underpinnings of quantum computing. I need to learn about the specifics of quantum programming for quantum computers. I still have to pull out the piece of the problem that I believe is quantum friendly and program that. And then once I'm getting results, I need to tune that, and that people find is a lot of work. By contrast with Mukai, it's roughly a week. I learn the API. Those are concepts I already am familiar with. I define and submit the problem. I process and return the results. There might be a little tuning to be done, but really this is a few days compared with 4 to 16 months, which is what we hear from industry experts. So this is a dramatic difference in how many people are going to make sense, going to be able to use these QPUs. So a few practicalities. So Mukai is a constrained optimization service. By that I mean it only does constrained optimization. There are lots of things that quantum computers can possibly do beyond constrained optimization. We're not focused on those for now. We're only focused on constrained optimization. It's a service running in the cloud, like a lot of things these days. It delivers strong performance today, classically, and we're also gearing up for strong performance tomorrow from blended quantum classical. And I'll say again, subject matter expert APIs. There are the two different APIs are constraint optimization and graph. If you're interested in performance, this archive, the URL for this archive paper that we did last year goes into great detail about our graph partitioning performance and how we have some state-of-the-art results there. So that may be interesting. You might be wondering, how big a problem can I solve with this? And what we've done to date is up to 110,000 variables and 8,000 constraints. That was running classically. I may have said already we have support for Rigetti, IonQ, and D-Wave QPUs today in the released product and others coming soon. Today, also, if you're using a QPU, the problems have to be limited to the size of the QPU for quantum execution. But we're working on something there, so watch this space. Lastly, if you have interest, questions or details about the APIs, our documentation is online. Please feel free to go look at that. And with that, I will turn it over to Raouf for the constraint optimization demo.
Okay, thanks, Steve. So I can't share the screen for.
Okay.
Probably need to transfer.
Right. Raouf. So I did that with Steve. And Steve, can you make Raouf a co-host?
Give me 1 second. Where does one do that?
I was looking at the panelist list on the right side of the screen.
Ah, yeah, okay.
And if you right click, I think.
Co-host.
Yeah.
Yes, okay, just did that. So you should be co-host now, right?
Works. Can you guys see my screen here?
Yes, we see your screen.
Okay. Well, thank you again, Steve, and thank you, Faisal, for the introduction and for the invitation. So today I have a very simple goal. Is I will be introducing Mukai API for solving constraint optimization problems. And my plan is I will be doing so using an example. And you will see I will be solving this example classically and quantum mechanically, using 4 different backends here. I'll be using D-Wave, Rigetti, and IonQ. I'll be solving the problem in 3 different ways, using quantum machine and VQE and QAUA. So let me first start by introducing the problem. So this is a problem, optimization problem, in the context of power grid optimization. So here we have n power plants to be assigned to n regions in such a way you minimize a certain cost function. So this function the cost function is a product of 2 quantities. The cost of transporting 1 unit of energy from a given location to another, and the number of units of energy to be transported. You can easily see we have n squared possible assignment to be or the n squared binary variables xpi, which represent whether plant P is assigned to location I. Now, if you don't understand the problem, that's okay. But what I want you to appreciate is this is a constraint optimization problem. So mathematically, this looks like this expression here, where we have an objective function to minimize a certain number of constraints to satisfy. The constraints here are just ensuring that one and only one facility is assigned to a given location. So, and this is a picture representation of the problem. So let me be more concrete here and consider the case when we have only three plants. So the objective function here is a 9 by 9 matrix. This is how it looks like. This is an example, and the constraint matrix is a 6 by or but it's a set of all constraints you'd like to set up. So we have here the right hand side of the constraint as the last column. This is the right hand side I'm expressing here. So now the next step I'll be solving this using Mukai, and mathematics. And the mathematics behind is the familiar Lagrange formulation. So where we have a penalty alpha, which taxes you whenever you violate a constraint. Okay, so let's solve this using Mukai. So the very first thing I do, I will be importing acquire. This is the specific API for constraint optimizations. So and the way I do it, I just be using sample Lagrange optimization. This is the only function I'll be using throughout my demo, and I will be calling this particular function on the objective function I defined before, and the constraint. And here in this case, I'm solving this classically using our classical solver. This is, of course, this is a tiny example for our classical solver, and as Steve mentioned, our classical solver is capable of solving very large problems. But this is for the sake of introducing the quantum samplers. So when I solve this, I get an answer, something like this, which is just saying that, for instance, the plant 1 is assigned to region 1, and plant 2 is assigned to region 3, and so on. And you can, and here I'm just showing the evolution of the Lagrange multipliers, and you see this is the very first iteration. So this is the initial set of the multipliers. And here we're not satisfying any constraint because we just started. And as we move forward, we see actually you start satisfying constraint. And if you go all the way down, you see we satisfying all the constraint. And these are the final values of the Lagrange multipliers. So again, this is the familiar Lagrange multiplier approach to solve constraint optimization. And this is how we solve it classically in Quire, in Mukai. So now I'll be doing, for the rest of my talk, I'll be doing exactly the same thing, but I will be solving this using quantum mechanically. Okay, and the very first system I consider is D wave advantage. So again, I have exactly the same syntax as before. This is what I promised you. And the only change here is the sampler. So sampler now is D wave advantage. This is an extra parameter which specifies which sampler we would like to use. By default is the classical solver. And I solve this, I'll let this run. And I compare with my classical solution and say, this is for sake of correctness, I'm satisfying, I'm getting exactly the same solution. I'm also seeing, and I'm doing, and then again, play the same game here, solving the same problem on the Wave 2000Q. Again, here, this is exactly the same syntax, the same function using a different sampler. This is what it is. And again, I'm just here, the stands for me comparing what I'm getting to the correct solution. Yeah, and here also I'm seeing I'm having the nice behavior, the convergence behavior, Lagrange multiplier. This is nice. So I start again with the initial seed of the multipliers, and my multipliers converge to these particular values, which and then I have satisfaction of the constraint. Okay. So so now if you want to use, let's say, Rigetti or gate machine, again, here, I'll be using the same syntax again. I'm using sampler now. I set the sampler to bracket Rigetti and run my sample Lagrange optimization. I get an answer. I compare it again, and I have again the nice evolution. So now in here in this particular case, this is a gate machine. So by default, VQE is being used here. And this is the generic ansatz being used here. So now, if you want to run this run QAUA, so again, you will be using, of course, the same function because we're still solving a Lagrange optimization. The only parameter you tweak in this case is the parameter algorithm, and then you specify it's a QAUA. So and you let this run again, and you get the same answer as before. Now you play the same game with INQ, which is also available by setting the sampler to bracket INQ. Now my last example is where again I'm playing the same game. I'm solving this exactly the same problem. Now, like here, the goal is to quickly show the different parameters you can tweak. Let's say this is one of parameters, setting choosing the algorithm, but also you want you can also tweak or change the classical optimizer you're using within QAUA and the different options you feed this classical optimizer. But of course, you can control the depth of the QAUA VQE, and you can also control the number of shots. So these are the different parameters you can tweak and play with. Of course, they come with default values, and these are the values I have used before. So this is my last example. So here I'm providing a link here for more documentation about Mukai API, and if you go there, you find all sorts of information to use the features and I presented today. And also you can find examples and more examples. And this is, for instance, these are the different parameters we have for QAUA and VQE. And the same we have, and these are the parameters we have for DUA. So this is my last slide. So thank you for your attention.
Wonderful, thank you, Raouf. And I think Mark is up next.
And once again, we need to figure out how to share the screen.
Oh, so
Steve could do that, right, Steve?
Yes.
There we go.
So actually, I was going to interject here for a second.
Sure, Steve.
So just to, so I think the key points here are, so Raouf has introduced our Mukai API for solving constraint optimization problems. Whoops, sorry, forgot to turn my video back on. And we considered the example of facility location, allocation, and energy systems optimization. He showed solving it both classically and quantum mechanically using different backends, different algorithms, and we reached optimality in all of them. So obviously that's possible for small problems, but hard for big problems. So now we want to switch gears to Mark Wainger, who'll present about community detection. This is a higher level and more focused API that under the covers is constraint optimization, but solves a higher level problem that early users are telling us is high value. So Mark, off to you.
Thanks, Steve. Yes, as Steve mentioned, I'll be discussing community detection and our implementation of it. Community detection is a pretty recent development. It's a nice algorithm for understanding the structure of complex data. Really, the seminal papers are written by two people, Newman and Gervan, starting in the early 2000s on their big contribution was that detecting communities is an optimization problem, and the quantity you're trying to optimize is a metric called modularity, which measures how well a given community is connected together, and how so you're trying to maximize the connections within a community and minimize the connections between communities. You can see a simple example of that from their paper, where these are nodes in a network or a graph, and these nodes are all pretty tightly connected, and the connections that go across a given community are few. So you want to maximize the connections within a community and minimize the connections between communities. And the way that you calculate the modularity is you calculate a measure of how well the nodes are connected together, and then you subtract off what they call a null model, which means you assume that the graph, each node has the same number of connections, the same degree, but the connections are randomized, and therefore there's no communities present. And so it's the modularity is the difference of those two terms. And they studied modularity with one of the sample graphs they use is the Karate Club, which is a club made up of 33 individuals and some connections between them. Before we look at, so we're going to look at the Karate Club, but before we do that, I wanted to mention a second paper, which was written about 1.5 years ago by some scientists at Los Alamos, which is an implementation of the technique that we use to solve community detection problems. And the typical implementation of the original Newman-Durbin approach is a local optimization, where you start with, one way to do it is to start with all the nodes in separate communities. And then each time step, you try to join the two communities together that contributes the largest increase in modularity. And you keep doing that procedure until you can't join any more communities. And so that would typically give you sort of a upper limit on how many actual communities there are, but because it's a local optimization process, you're not guaranteed to find the optimal community structure. What the people at Los Alamos came up with is a global optimization procedure. And so you basically put for each node in the graph, if you want to find 5 communities, you set up a matrix that has 5 elements for each node, and one of so the objective function is to maximize modularity, and the constraint is that each node can only be in one of the 5 communities. And so the size of the problem scales as the number of nodes times the number of communities you're searching for. So that certainly trying to fit into a QPU, you can only do a couple of nodes. You can do a fairly large size problem in our Mukai software server, because say you have 10,000 nodes, you can easily look for 10 communities. That could be 100,000 variables. We can solve problems of that size. As an example, they provide that the Lionel folks provide in their paper is this very simple protein that's made up of 7 amino acids. And if you set up a graph based on the force of the atomic level connections between each atom in this complex molecule, and you do community detection on that, the communities that are detected map exactly to the 7 amino acids that make up this protein. And the modularity of this solution is about 0.75. So that's modularity varies between 0 and 1. Modularity of 0.75 is very high, and that's typically associated with inorganic kind of problems like this. Your typical social network, where you're looking at people and connections, might have a modularity of 0.3 or 0.4. So it's because there's more noise in the system there. So here we get down to some code. I'm going to use network X to create a graph based on the karate club. And if I run this, you can see that the edges in the graph, the nodes in the graph, the people are represented as digits from 0 to 33. And the edges connect two different people. This empty dictionary could contain a weight if this is a weighted graph, but in this case, it's an unweighted graph. And you can see the, so this is a plot of the graph. You can see each node and the connections to the other nodes. And then Network X also has a community detection algorithm built into it that's Gerben-Newman local optimization. So if I run that, what it does is it starts with all the nodes in one community, and then each time step, it breaks it up into one additional community. So the very first time step, it found these two communities, and it calculates a modularity based on that. So it divides up the existing communities into one more, where it's maximizing the increase in modularity. And you can see that at the beginning, the first step it does is it moves node 2 into a separate community from nodes 0, 1, and 3. It turns out the optimal solution for this problem has node 2 in with 0, 1, and 3. So at the very first time step, this is a locally optimal decision, but it's not a globally optimal decision. So they can never get back to the global maximum once it makes this step here. You can see the modularity actually goes down a little bit when it comes up with 3 communities, goes back up when it gets to 4 communities, and the maximum modularity is achieved with 5 communities, goes back down. So you would say that the best answer here is 5 communities. Well, it turns out the optimal answer for the karate club is 4 communities. And if we run the global optimization version, which I'm running live right now, so you can see we uploaded a problem and we're working on solving it. And so for 3 communities, we got a modularity of 0.402, which is better than the best modularity that the Gerben-Newman algorithm found. For 4 communities, we got a modularity of 0.4198. This is actually the optimal solution. And then when it ran 5 communities, you can see one of the communities is blank. So even though you asked for 5, it says, oh, the global maximum occurs with 4. So I'm going to give you the 5th one as just a black, empty community. And here's a graph of the colored with each community, so you can see how the nodes separate into the 4 natural communities. You can also see that, for example, 4, 5, 6, 10, 16 is a community that one of the 4 communities. And if we look back at the Gerben-Newman algorithm, it also identified that community. So it doesn't give you totally wrong answers, but it does give you a non-optimal answer. And we found the optimal answer here. Okay, so that's fine. And this is an example of what's called a unipartite graph. There's only one kind of node in this graph, the members of the karate club. And we just take it for granted they're somehow connected. Turns out most graphs are what are called most interesting graphs are what are called bipartite graphs. They have 2 kinds of nodes. For example, these karate club members are presumably connected because they went to some karate club meetings together. And so bipartite graphs are a bit more complicated to analyze, and we're using, in particular, the modularity metric has to be different than a unipartite graph. There's a paper written by Michael Barber published in 2008 where he proposed this different modularity measure that's appropriate for a bipartite graph. And he studied one of the classic graphs in this field called the Southern Women Graph. So this is a network of Southern women, 18 women in the Southern United States who attended 14 different meetings. And so the women are connected by which meetings they attended. And to look at this graph in a little bit more detail, we can see that the nodes in the, so this graph is also available in Network X, the Davis Southern Women graph. The nodes consist of the names of the women and an indicator that this is a bipart. So this dictionary says this is a bipartite graph, and all the women are in mode 0 of the graph. And then down here, you can see the different events, the different meetings they went to between E1 and E14, and they're in the one mode of the bipartite graph. So they're separate the women and then the meetings they attended to. And the edges in this graph consist of one woman and one meeting. And again, it's an unweighted graph, so there's nothing in the edge dictionary. And if we look at this graph, what you can see is the women are listed on this side. The meetings they attended are listed on this side. None of the women are connected together directly. They're all connected to the events they attended. None of the events are directly connected. They are all connected to the women who attended that event. So that's a standard way of looking at a bipartite graph. And so that's also the reason the modularity metric has to be different. Because for a unipartite graph, when you randomize the edges, any two nodes could be connected together. But in a bipartite graph, when you randomize the edges, you can't connect two women together or two events together. So the null model is different for a bipartite graph. So we implemented the Barber method for calculating modularity, and we can go ahead and run that. So it's now doing community detection on the Southern women. We found 3 communities with a modularity point 3452. When we do 4 communities, we get 3455. So very small but measurable increase in modularity. And then if we try running 5 communities again, we get an empty community here. So it only finds 4 with exactly the same modularity. And we can look at the results. So it's color coded so that you can see Sylvia is also in the same community as events 10, 13, 12, and 14. And again, this is the global optimal solution that's presented in the literature and that we can duplicate by setting up and solving a constrained optimization problem. Then finally, the last step in the analysis is we look at, so this is fine to analyze a small graph like this, but in general, there could be a large number of nodes too big to solve in a single optimization problem. A typical example might be that you have patients here and the medical variables. They have blood pressure, weight, body mass index, things like that. So there's a fairly small number of medical variables, but you might have 100,000 or 500,000 patients, too many patients to set up a problem and solve it. And so the way that you can resolve that problem is through doing a mathematical procedure called projection, where you get rid of all the patients and only consider a graph consisting of the medical variables. And so there's another paper here that came out last year, written by a gentleman from University of Exeter in the United Kingdom, which looks at the modularity for the projection of bipartite network onto a unipartite network. One of the things you want to look at is how well did you recover the original bipartite community structure from your unipartite projection. And so that it's somewhat difficult to measure how well communities compare. And he gives a simple example. So there's 3 kinds of nodes: the squares, the triangles, and the circles, and you're trying to detect the community. So the correct answer is you have 3 communities, one for the squares, one for the triangles, and one for the circles. But here's 2 examples of inexact community detection. In this case, we have 5 communities. In this case, we have 2. So there's one standard measure of how well 2 solutions are similar is called normalized mutual information. And so Arthur breaks down mutual information into 2 separate measures. One is, do the communities you find, do they all consist of the same the same kind of node? And a second measure is, does a community consist of all the nodes of a given type? So in the top example here, every community only has one kind of node. However, all the nodes of a given community are not present together. So it gets high marks on the one measure and lower marks on the other. Here, we've got all the nodes of a given type are together, but this community is incorrect because it's mixed 2 different types of nodes. So both of these have approximately the same mutual information, 0.8, even though the community structure is very different. And so he points out that you really need to look at the different dimensions of community matching to see how well you're doing, as well as providing the analysis of how to calculate modularity for projected bipartite graph. And then there's a second paper written last year, so this is very current stuff. I think one of the best contributions is the title of the paper, "Is it correct to project and detect?" So they made a nice little poem there. How weighting unipartite projections influences community detection. So to explain projecting a little bit better, you can see here's the bipartite graph. You've got 2 kinds of nodes, and each circle is only connected to squares, and each square is only connected to circles. When you project out these rectangles, you end up with a graph that only has circles. And the edges that connect the circles are, if 2 circles are both connected to the same square, then they get a connection in this projected graph. And you can see everything is connected except 2 to 5. There's no connection between 2 and 5. And on the right-hand side here, you can see that circle 2 only connects to square 1 and 2. Circle 5 only connects to square 5. So there's no common square that both 2 and 5 connect to. That's why there's no connection here. This is known as a binary projection. It says if there's any connection, any shared connection between 2 nodes, they get an edge here. This is a weighted projection known as simple projection, where the number of shared nodes is the weight of this edge. So 1 and 4 share a large number of nodes. 2 and 4 have less connected nodes in common, so they have so the weight is less. Turns out that this is sort of the most obvious way to weight the nodes is by how many mutual connections they share. But when you calculate modularity, so they're basically the edge is weighted by the degree. When you calculate modularity, you square the degree, and so that the modularity calculation overweights the nodes with high degree. So there's a second kind of weighting called hyperbolic projection, where you scale the weights divide by the degree, and a third type called unary projection, where you scale the weights by the degree squared, 1 over the degree squared. So you're sort of normalizing the weights in different ways. And then they got some random walk, some other kinds of projections, which we don't need to get into. And then, so this is this stuff is what we're currently working on. So it's not built into Mukai yet. So you can see a lot of code here to implement it. This is the scaling part here. And if let's see, I'm set up to do simple scaling. So if I run it, I can calculate communities based on simple scaling. And the answer I get, it only finds 2 communities. So 2 communities are empty. We know the right answer is 4. So if I go back and change from, so the authors of this paper looking at the different scaling types, they found that hyperbolic works best for over a wide range of random graphs they studied. But for this particular Southern Women graph, it turns out that that unary scaling works best. So if I use unary scaling, then I get back, I do in fact find 4 communities in the graph. And so it's a better weighting scheme. And that's the end of my presentation. So hand it back over to Faisal.
Wonderful. Thank you, Mark.
Mark,
Yes,
there was a question from the Q&A. It says, which reference time, event time is on use when the 4th community emerges from the optimization of 3 communities?
So that was the Gervin, I believe the Gervin-Newman, let's see. So we're, let's see. No. Yeah, so this year, so can you sorry, Steve, can you repeat that question again?
Yeah, let me see if I can just cut and paste it into the chat. Oops, sorry. Which reference time, event time is on use when the 4th community emerges from the optimization of 3 communities?
Yeah, I'm not sure I understand that question fully. If it's referring to this Gervin-Newman, so each step it adds one, it splits things up into one additional community, and so the step 3, so modularity is increasing here, increases again, so it goes from 3 to 4 to 5. Once you get to 6 communities, modularity goes back down and it continues going down from there. So you're basically looking for how many communities gives you the maximum modularity. And so for the Gervin-Newman algorithm in network X, it finds 5 communities. What we do with our global procedure is we say, okay, if try to find 3 communities, it gets an answer which has a certain modularity. And then we say, all right, go look for 4 communities, it has a bigger modularity. All right, go look for 5 communities, and it returns back. The 5th one is empty, and so you just have the 4 communities with the exact same modularity. If I ask for 6 or 7, it always comes back with 4 at this point. So the technique for this, so the number of communities isn't known beforehand for a given graph. And so that's one of the things that comes out of this type of analysis is you just try different numbers of communities and see which gives you the maximum modularity. And for complex graphs, you might get, the k+1 or k+2 might have some solution where all communities have some members in it, but the modularity will be lower, and that's how you know that you found the correct number of communities. It's the one that maximizes the overall modularity. I hope that answered the question. If not, I can try some more.
Yeah, thanks, Mark.
Sure.
Steve, may I suggest that you perhaps address some of the questions that appeared on the Q&A?
Sure. So as people, yeah, are there any of those in particular that you think of? So for those of you who may not be super Zoom familiar, there's a Q&A that I'm guessing all the attendees can see. Is that right? And so we've been answering those. I mean, if there are particular ones.
I was thinking perhaps the question about experts at JP Morgan, IBM, etc.
Yeah, so right, it is a good question because you know, there are people who jumped into quantum computing 2 years ago or 5 years ago, or whatever, and they've learned a whole lot about low-level programming of QPUs. And does this mean
Sorry,
that?
let me just read the question really quick. So,
Oh, sorry,
yeah,
sorry.
just yeah, it's very clear. The question is, it's very clear that it's an incredible tool, referring to Mukai, for non-quantum experts. How could it help quantum expert as in JP Morgan, Exxon Mobil, IBM, etc.? Thank you, Steve.
Yeah. So I guess to me, there's a handful of answers. Maybe first, if you are one of those experts that knows low-level details, Mukai implements optimizations both at a high level and a medium level that are bleeding edge, that are very difficult to implement in a way that you can use all day, every day. And that's the way we implement them. So there's quite a bit of work to go from an algorithm and a paper to working software, you know, working all day, every day. So we've done that work. Not that we've done it for every algorithm on the planet, but we've done that work for a number of algorithms. Some of those are from the outside world, some of those are our own development. So even if you know everything about the QPU, there are other optimizations that can benefit you that are in Mukai. A second one is even if you're that low level, if you're aware of those low level issues, you might easily want to compare QPUs, and maybe you've spent a bunch of time on a Rigetti QPU, but you really care about, you're thinking, well, maybe there's this new one from Xanadu. Maybe that's the one I should be focused on. Well, that's a whole bunch of work, of extra work to learn about the Xanadu QPU, target your problem to it in a, where you're using that QPU very effectively. And so just comparing QPUs can be a lot of work. And that's something that, in Mukai, you can just change it. You specify, as Raouf showed you, you specify, here's my sampler, it's D-Wave Advantage. Here's my sampler, it's IonQ. And it's that easy to switch. So we think that's an advantage even for low-level developers. And the last one is, yes, there are low-level developers who are expert, and there's a pretty small group of those people. And if you go to an Exxon Mobil or a JP Morgan or an IBM, they have a lot of problems, a lot of applications that they want to benefit from quantum computing. And there are just not enough of those experts to solve all those problems, to port, if I can use that word, to port those applications to quantum. So if you're going to do this, if you're going to actually get a number of applications, doing it in a low-level way just doesn't seem sustainable. So that would be my answer. Awesome.
Thank you, Steve. There's another question that just popped up on the Q&A. Perhaps we can address that live. It says, so essentially it's an API, it being Mukai, that helps bridge classical and quantum, mostly gate-based. How is it different than Q#? And second, is it only tested on annealer?
Right. So Raouf showed you running on 2 generations of annealers from D-Wave, as well as running on IonQ and Rigetti gate model processors. So the answer to that is no, it is on annealers, but it is also on gate model. How is this different from Q#? So with the caveat that I'm not an expert in Q#, so number one, we're focused on what we call a subject matter SME API, subject matter expert API. So this is if I'm a protein designer, this is a, I can think in terms of constraints and an objective function. That's something that those are concepts that are familiar to me. And I can just program in those terms and run on a quantum computer. I don't believe that's possible with Q#. That could be my ignorance. So that's part of it. I would also say, as I mentioned a minute ago, we have a bunch of optimizations like in the process of going from a constrained optimization problem to either a QBO or when solving the QBO via QAOA or VQE. We have a bunch of optimizations there that simplify the problem, shrink the problem, make it more easily solvable in various ways. And to my knowledge, those aren't implemented in Q#.
Steve, I also have something to add on to that, which is that the problems that I was demonstrating, which were very small community detection problems, are already too big to fit on any of today's QPUs. With the possible, we might be able to squeeze looking for 3 communities into the biggest D-Wave advantage chip right now. So the way that I solved all the problems that I demonstrated today was on we have an AWS server, 96-core AWS server running our proprietary version of what's called QBSolve, which was originally developed at D-Wave by our Chief Technology Officer, Mike Booth. So QBSolve is a classical software QBO solver. It does a whole bunch of random stuff to find the optimal solution for a given QBO. That's the technology that we're using to solve problems of up to 100,000 variables in a fully connected QBO. So that would require, a D-Wave quantum annealer machine that would have, on the order of 1 million qubits. So that's a couple of years away probably. And we can solve those problems today. So the idea is that you can set up optimization problems in a quantum compatible manner, but solve them today, get answers today that are useful answers. And that will transparently, as QPUs become more capable and get larger, the same software that you've written that you're solving today in a classical, approximately solving it with a classical machine, then you can just in exactly the same manner solve them on tomorrow's QPU.
Excellent. Thank you, Steve and Mark. There are a few more questions. I'll leave it up to you guys, depending on your time constraints. I know it's a weekend, but still it's a work day. So if you feel like addressing some of them, please go ahead. Otherwise, perhaps you could share a email link, email contact on the common chat for everybody who might be interested in getting in touch with you guys.
Yeah. So give me 1 second and I will do that. So I think we've addressed that one. I think we've answered the Q#. An example of optimization. I don't know, Raouf, do you have one that would come to mind that we'd be willing to
I was about to share the notebooks,
okay.
the one online.
So the question, how do you recommend getting involved in working in quantum outside of general programming for your own fun? I guess, so meetups like this are a good place to start, honestly. There's a lot of excitement. I would look for, let me think.
You basically need to be trying to solve a problem that is amenable to using a quantum computer to solve, which these days, a lot of it, I mean, the most advanced part of that are these optimization problems where you're trying to minimize or maximize something subject to some constraints. And so a lot of finance problems involve optimization. You want to, maximize your return subject to constraining your risk, or you want to minimize your profits subject to how much of a product you can build different kinds of products. There's a constraint on how many of each product you can build, and so what's the mix of products that maximizes your profitability. So there's all sorts of optimization problems, and you have to be facing one in either in your personal life or in your professional life, and then you can it should be pretty easy to translate to a quantum friendly implementation of it.
Wonderful. So the panelists, please let me know if you have any other questions you would like to address. If not, we can wind up and call it a meeting.
Well, we're getting some thanks in the chat, so I think we did a good job, Faisal. Hopefully we provide some entertainment for everybody.
Yeah,
it looks that way.
Great.
That's awesome.
Well, and it looks like people are kind of heading for the exit, so.
Party's over.
That's right.
I could see the number of attendees going down, so sure, wonderful. Yeah. So let me just thank you, everybody, all the panelists, Steve, Mark, and Raouf, for this wonderful presentation and informative presentation. And thank you to all the attendees for making time, especially those who are on the Pacific time zone or earlier, for making the time to come and meet us here so early in the morning. I should thank Association Quantum again for sponsoring this event, and our friends at Washington, D.C. Quantum Computing Meetup Group, who are collaborating with us in organizing such events. And please, keep an eye on the Middle East and South Asia Quantum Computing Meetup Group for more further events to come. And I hope to see you there. Thank you very much.
Thanks again for hosting us, Faisal.
Thank you.
Cheers.
Take care. Bye-bye.